We said before that probability theory is a tool that helps to guide our decision in the ex-ante stage before uncertainty is resolved. Well, in a lot of situations, between the ex-ante stage and the ex-post stage, there may be one or multiple interim stages. That is, information is often released step by step. When some information is released, but the uncertainty is not completely resolved, probability theory is still helpful. And in that situation, we want to consider conditional probability measures. To define conditional probability, we consider first two events, A and B. These are events in the sample space S. And we want to figure out the probability of event A, given that we already know event B occurred. Okay, that's probability of A given B. What should be this conditional probability? I will write down the conditional probability formula and then explain the intuition behind it on the next slide. Conditional probability of A given B is a ratio, it's the ratio of probability of A intersection B and probability of B. Now the numerator is also called the joint probability of the event A and event B. And the denominator may also be called the marginal probability of event B. Now, why is conditional probability defined in this way? We can try to get some intuition by looking at the Venn diagram. Now, suppose that ex ante, before any information is released, this is the Venn diagram that describes the relationship between A and B and also our sample space S. Right? Now there is no information, so any outcome in the sample space S is possible. Then in the interim stage, we got some new information that says B occurred. Okay, so we know some outcome, we know that the outcome that occurred must be in B. Okay, that's the piece of new information that we get. What that means, we can eliminate all the possible outcomes outside of B. That's we can eliminate everything outside of B. Now B becomes our new sample space. And this area is a intersection B, which is the same as this intersection area on the left graph. Now B is the new sample space. The new information just tells us that B occurred, but it doesn't tell us anything about what happened inside of B. It doesn't contain, the new information doesn't inform us about the relative probability of A and B and the probability of B, because the new information is not informative about what's inside B. If we want to define the conditional probability given B, we might consider some intuitive axioms. The first axioms that's intuitive to us is probability of B given B equals 1. This is quite intuitive because with the new information, the sample space reduces to B. So B is the new sample space. Given that B occurred, therefore the probability of B given B should be 1. And the second axiom that might appear intuitive to us is that the new information doesn't change the relative probability of A and B, because the new information doesn't inform us about the relative likelihood of the outcomes inside of B. So the ratio, the relative probability before the new information is available is this, P A and B over PB. And after the new information is released, the ratio becomes the conditional probability of A and B over the conditional probability of B. So this relative probability is not changed by this new information. So this is another intuitive axiom that we might want to impose on the conditional probability. And we add on top of these two axioms a convention that we conventionally write probability of A and B given B just as P of A given B. That's because given that B occurs, only the elements in A that are also in B can occur. So given that B occurs, A and B, these two sets really are not different in any meaningful way. So we can just treat these two notation as equivalent. And so with this convention and these two intuitive axioms, we can derive the conditional probability formula. P of A given B is P of A and B over P of B. Right. So this is not a rigorous derivation of the conditional probability formula, but it gives us some intuition behind it. Let's now consider a simple example of conditional probability. In this example, there is a college graduate, Lily. Lily interviewed with 5 firms for a new job, and she feels equally good about the 5 firms. So she thinks that the 5 firms are equally likely to make her an offer. Now, a firm called Lily to make an offer when Lily was out, was not at home. Her roommate picked up the phone and got the good news. When Lily came back, the roommate told her the good news, but unfortunately, the roommate forgot which firm had called. So what's the probability of any of the firm to have called? Then because Lily felt equally good about each one, the probability of the caller being each of the firms should be the same. So ex ante, the probability of each of the firm should be the same because Lily felt equally good about each of them. Now this firm BA1, BA2 are 2 Boston accounting firms. The firms NA1 and NA2 are 2 New York accounting firms. And the firm BC is a Boston consulting firm. Okay, so A is accounting, C is consulting, B is Boston, and N stands for New York. Okay. Now, Lily is not satisfied with her roommate's relay of the message to her because she doesn't remember which firm it was. So the roommate thought and thought. She remembered one piece of information now. She remembers that the firm is in Boston. but she still doesn't remember which firm it was. So here is the new information. The new information is that the firm that called was a Boston firm. So the new information restricts the sample space to the set B that include all the Boston firms. Now, what is the probability that the firm is an accounting firm? Given the information that her roommate just released to her. Let's say this set is A. We now use the conditional probability formula. That's A and B, probability of A and B over PB. The set A and B would be the two Boston accounting firms. And the set B is the three Boston firms. Using this equal probability setup, we find that P A and B is 2 over 5, and probability of B is 3 over 5. And the conditional probability of the firm being an accounting firm, given that it is located in Boston, turns out to be 2/3. Now that we have learned conditional probability, we can revisit the law of total probability and write it in a different way. Remember the law of total probability, write PB, the marginal probability of B, as the sum of two probabilities, as the sum of probability of A and B, plus the probability, the sum of the probability of B can be written as the sum of two sets. Probability of B can be written as the sum of two probabilities. That's the sum of probability of A intersection B and probability of A complement intersect B. Using the conditional probability formula, we know probability of A intersect B equals probability of B given A times probability of A. And the probability of A complement intersect B equals probability of B given A complement times probability of A complement. So this is another way to write the law of total probabilities. And using this other way of writing the law of total probabilities, we can write down the Bayes rule, the famous Bayes rule. What is the Bayes rule doing? The Bayes rule handles the situation where you know the probability of an event B given each of a partition of the sample space. Now here in this example, we're considering A and A complement. A and A complement form a partition of the sample space. We know the conditional probability of B given A and given A complement. And we also know the probability of A, and as a result, we also know the probability of A complement. We know these three things. How do we calculate the probability of A given B? Just to have a concrete idea of what this is, consider the example that we talked about before. Now, suppose A is have antibody for SARS-CoV-2 virus. So now in this example, the S, the sample space S, is have antibody and tested positive for antibody. That's one outcome. And have antibody and tested negative. And have not have antibody and tested positive for antibody. And not have antibody and tested negative. So the sample space contains 4 outcomes. And the set A means you have the antibody for the virus, and B means you tested positive for the antibody. Suppose we know probability of positive test given that you have antibody is 0.99. And the probability of a positive test given that you do not have the antibody is 0.2. And suppose that before the testing you believe the probability that you have the antibody is 0.01. That's 1 in 100. Now that suppose you are tested positive, what is the probability that you actually have the antibody? The conditioning event is that you are tested positive for the antibody, and the event you are interested in is whether you do have the antibody or not. Now we can use the conditional probability formula, that's A and B divided by P of B. Probability of A and B can be written as B given A times P of A. This is using the conditional probability formula. For the denominator, we can use the law of total probability and write PB as PB given A times P of A plus PB given AC times P of AC. So this formula that connects the conditional probability of A given B and this ratio, that is the Bayes rule formula. Now, for the antibody test example, we can use the Bayes rule formula to calculate the conditional probability of A given B. Bayes rule says that this conditional probability equals probability of B given A times PA divided by PB given A times PA plus PB given AC times P of AC. We can now plug in all the numbers. PB given A is 0.99 times 0.01 and 0.99 times 0.01 plus 0.2 times P of AC.
P of AC, that is 1 minus P of A, right? So 1 minus P of A is 0.99. So that should be 0.99. Now it's easy to calculate what this is. We can first cancel out all the 0.99s, and you are left with 1 over 21. That's a little bit less than 5%. So that is an application of the Bayes rule. The Bayes rule we just introduced and used is the Bayes rule for a pair of events. There is a more general Bayes rule that applies in the situation where the sample space is partitioned into a group of n events, A1 to AN. So the events A1 to AN form a partition of the sample space, and the events have positive probability. All of the events in the group have positive probability, and probability of B also has positive probability. The situation is when we know probability of B given each of the events in the group that form the partition, and we also know the relative probability of each of the events in the partition. The Bayes rule tells us that probability of AI given B for any I from 1 to n equals a ratio with the numerator being PB given AI times P of AI, and the denominator being PB. But the PB can be represented as the sum J from 1 to n, probability of B given AJ times probability of AJ. This is a representation of PB. Now that we have learned conditional probability, we can talk about the independence of events. Independence of events is defined as follows. Two events A and B are independent if the probability of A given B is equal to the unconditional or the marginal probability of A. That's the new information about B doesn't change our evaluation of how likely A is. So B is useless for determining whether A occurs or not. So that defines independence between the events A and B. Using the conditional probability formula, this definition of independence can be equivalently written as P of A intersection B equals P of A times PB. These two are equivalent, which is easy to see by moving PB over to the other side. Then the left-hand side becomes the conditional probability of A given B, and that is exactly this definition of independence. This way of writing independence has another name. It's called the product rule. That's the probability of the intersection of two independent events equals the product of the probability of the two independent events. About independence, we have the following claim. If A and B are independent, then A complement and B are also independent. We can show this by first appealing to the law of total probability. P of B equals P of A intersect B plus P of A complement intersect B. That's the law of total probability. Now we know that A and B are independent. Therefore, P of A and B should be equal to probability of A times probability of B. Now let's move PA, PB to the left-hand side. We get probability of AC intersection B equals P of B minus P of A, PB. And we can factor out P of B, right? So we factored out P of B. We find that P of AC intersect B equals PB times 1 minus PA. But what is 1 minus PA? By the complement rule, that equals P of A complement. So this is by the complement rule. So this means that the probability of AC intersect B also satisfies the product rule, which means AC and B are independent. Similarly, AC and BC are also independent. That's A complement and B complement are also independent. The next concept of independence is a little bit more complicated. That's the independence of a group of events, independent groups of events. A group of events, A1, A2 to AN, is an independent group of events, is independent if any subgroup is also independent. To give you a concrete idea of what that means, let's consider an example where n equals 3. As we are considering a group of 3 events, A1, A2, and A3. This group of events are independent if the following 4 conditions hold. The 4 conditions are P of A1 intersection A2 intersection A3 equals P of A1 times P of A2 times P of A3. But this is not enough. We also need the pairwise A1 intersect A2, the pairwise independence between any possible pairs. So why does the independence of the group of events require so many equations to define? You might wonder whether these 3 pairwise independence implies the independence, the independence of the 3 events. Well, the fact is, it doesn't. Pairwise independence does not imply the independence of the group of events. Now let's consider an example that shows pairwise independence does not imply group independence. In this example, we consider 3 light bulbs in 3 separate rooms that have closed doors. You are outside of the doors, so you do not know which light bulb is on and which light bulb is off. Suppose that the light bulb being on is denoted by 1 and the light bulb being off is denoted by 0. Then with 3 light bulbs, there are 8 possibilities for their on and off status. These 8 probabilities are written here. So the sample space contains 8 elements. So that's all of them are on, all of them are off, 2 of them are on, 1 of them is on. Okay. Now consider the probability measure that gives the following probability to each of the outcome. That's PS equals 0 for 1, 1, 1. So it's not possible for all to be on. And 0.25 for all of them to be off. And 0.25 for each of the outcome in which 2 light bulbs are on. And the probability that only 1 light bulb is on is 0. Suppose that is the probability measure that we consider. Consider these 3 events. A being the first light bulb is on. Four outcomes are consistent with the statement that the first light bulb is on. And we call that set A, event A. And event B is the second light bulb is on. And the third event is the third light bulb is on. Now P of A, we can calculate what P of A is. P of A is the probability of 1, 1, 1. So that's 0. That has probability 0. 1, 0, 1 has probability 25, 0.25. 1, 1, 0 has probability 0.25. 1, 0, 0 has probability 0. So therefore, P of A equals 0.5. And we can do the same calculation for P of B and P of C, and they are all equal to 0.5. Now, what about probability of the intersection of A and B? The probability of the intersection of A and B include the element 1, 1, 1 and 1, 1, 0. And that has probability 0.25 because 1, 1, 1 has probability 0, 1, 1, 0 has probability 25. So that's 0.25. You can do the same calculation for P of B and C and P of A and C. So pairwise, the product rule holds. P of A and B equals P of A times P of B. P of B and C also equal P of B times P of C. P of A and C also equals P of A times P of C. Right, so pairwise independence does hold. But probability of A and B and C does not satisfy the product rule. What is the set A and B and C? The common element of A, B, and C is 1, 1, 1. So that's the probability 1, 1, 1. Probability of 1, 1, 1, and that is 0. That's not the same as PA, PB times PC. So the group independence does not hold for this probability measure. So this example demonstrates that pairwise independence is not sufficient for a group independence. One last point I want to make in this video is infinite sample space. Right? Previously, we have focused on the finite sample space case, but oftentimes we might encounter infinite sample space. There are two kinds of infinities. The first kind is countable infinity. So countably infinite sample space. And the second kind, as you can guess, is uncountably infinite S. Countably infinite S contains countably infinite elements. So what does that mean? It means the elements can be counted. Has, for example, S might be all the positive integers. Or uncountably infinite sample space include much more points. The elements inside uncountably infinite sample space cannot be enumerated. For example, as is the interval 0 to 1 on the real line. The real interval 0 to 1 is not countable. With either countably infinite or uncountably infinite S, we can define probability measures, but we need to modify one of the axioms for probability. To define a probability measure, we do not need to modify the first two axioms of probability, but we do need to modify the additivity axioms. The additivity axiom needs to be modified into countable additivity. Countable additivity is stated as follows. For any countable group of disjoint events, A1, A2 to infinity, the probability measure should satisfy probability of the union of all the events in this group equals the sum of the probability of each event. Strengthening additivity to countable additivity avoids some very strange probability measures. But it also causes some logical difficulties when the sample space is uncountably infinite. We are not going to go into that. We'll just know that when the sample space is infinite, we want the probability measure to satisfy countable additivity.